Theorem: if a series converges, its general terms tends towards 0 as n becomes infinity. That is, if the series is convergent, let the series is sigma an. If it is convergent, then the limit of this nth term is equals to 0. That is this theorem, right? But the converse is not true. How it is converse is not true, because if you have a term of the series which becomes 0 as n tending to infinity, then it said that the series also converges. But that is not true, right? Because the converse is not true, right? Now let us prove it. What is the proof of this? Let sigma an be a series. Firstly we let series, and the second we let the partial sum of the series, right? Sequence of partial sum is Sn. What is Sn? If a1 plus a2 plus an minus 1 plus an, right? These are the partial sum of the series. Now take Sn minus 1 terms. These are Sn minus an minus 2 plus an minus 1, right? These are less than 2 nth term. So taking subtraction of this Sn minus 1, which is equals to an, right? Which all terms are goes out and this becomes only an. Since the series sigma an is converges, so Sn also converges. As we know that sigma an is converges, then this implies that Sn is also convergent, because we take sigma an is convergent, then the sequence of partial sums is also convergent. Now let us define that the sequence of partial sum is converges to S. Then this says to be, if you have one term less than this sequence of partial sum, this also converges to S. This implies that an term, what is an term? An term is that Sn minus 1, right? So taking limit of this becomes 0. This implies that anth term is equals to 0 as n tending to infinity. This condition is true for convergence is necessary, but not a sufficient condition, right? Consider the harmonic series. What is the harmonic series? Sigma 1 over n, which is this 1 plus 1 by 2 plus 1 by 3 1 by n and so on infinity. Now let the term an 1 by n, which goes to 0, but this series is not convergent. If this series is harmonic series, this is divergent series.